Welcome to our advanced physics series. Today, we are diving into the fascinating world of quantum theory, starting with the fundamental nature of light and the photoelectric effect. Let's begin with the core idea of quantum theory. It states that light isn't just a continuous wave. It is made up of discrete, indivisible packets of energy called photons. When a beam of light hits a metal surface, each photon interacts with only one electron, transferring all of its energy to it in a strict one-to-one exchange. But does every photon knock an electron loose? Not quite. Every metal has a work function, which is the minimum energy required to overcome the attractive forces of the nucleus. If a photon's energy is greater than this work function, it is absorbed, and the electron can escape. If it is less, the photon is simply rejected. This brings us to a very famous equation. The total energy of the incoming photon, represented by HF, is split into two parts. First, it pays the toll to escape the metal, which is the work function omega naught. Any leftover energy becomes the maximum kinetic energy of the escaping electron, represented by 1/2 mv squared. We can also write this equation in terms of wavelength. Since the speed of light c equals frequency times wavelength, we can substitute frequency with c over lambda. This gives us hc over lambda equals the work function plus the maximum kinetic energy. This form is incredibly useful when experiments measure the wavelength of light rather than its frequency. How do we know this quantum theory is true? One piece of evidence comes from optical spectra. When an excited electron drops from a higher energy level to a lower one, it emits energy at a very specific wavelength, creating a distinct line in the optical emission spectrum. This proves that energy is released in discrete photon packets, not a continuous stream. Further evidence is found in X-ray line spectra. When electrons transition between inner shells of a metal target, they release discrete packets of energy, or photons, that are characteristic of that specific metal. Additionally, the very fact that photoelectric emission requires a specific minimum energy perfectly aligns with the concept of individual photons interacting with individual electrons. Let's look closer at how photoelectric emission proves the quantum nature of light. Classical physics predicted that brighter light would give electrons more kinetic energy, but experiments showed otherwise. Increasing the intensity of light only increases the number of photons hitting the surface per second. The energy of each individual photon stays exactly the same, so the maximum kinetic energy of the emitted electrons does not change. However, increasing the intensity does have one measurable effect. Because a brighter light means more photons are striking the metal surface every second, more electrons are knocked loose per second. This means the rate of emission, or the photocurrent, increases directly with the intensity of the light, exactly as observed in experiments. Now, what happens if we change the color or frequency of the light? According to quantum theory, increasing the frequency increases the energy of each individual photon. Since the work function is constant, a higher energy photon leaves more leftover energy for the electron. Thus, the maximum kinetic energy of the electrons increases with frequency, another perfect match with experimental data. Let's formalize some key terms. The work function is defined as the absolute minimum amount of energy that must be supplied to a metal surface to discharge its outermost electron. You can think of it as the binding energy, the exact amount of effort required to overcome the attractive forces of the atomic nuclei holding that electron in place. Next, we have the threshold or cutoff frequency. This is the minimum frequency of light needed to cause emission. If the light's frequency is below this, no electrons are emitted, no matter how bright the light is. We also use the term stopping potential. In a circuit, this is the minimum negative voltage we must apply to the receiving electrode to repel and completely stop even the fastest emitted electrons. Finally, underpinning all of this is Planck's theory. Max Planck proposed that the energy of a photon is directly proportional to its frequency. This gives us the foundational equation E equals hf, where h is Planck's constant. This simple relationship is the bridge between the wave property of frequency and the particle property of discrete energy. Let's apply these concepts to a worked example involving a vacuum photocell. We have a cathode illuminated by monochromatic light of wavelength 4.4 times 10 to the negative 7 meters, and a work function of 2 electron volts. As a potential divider slider moves, making the cathode more positive relative to the anode, it creates a retarding force. This slows the electrons down, causing the current on the microammeter to gradually decrease to zero. To find the exact voltage where the current ceases, the stopping potential, we use our photoelectric equation. First, we convert the 2-electron-volt work function into joules. We plug in Planck's constant, the speed of light, and our wavelength to find the photon energy, subtract the work function, and set the remainder equal to the electron charge times the stopping potential. Solving this gives a stopping potential of 0.8253 volts.
What if we change the conditions? If we increase the light's intensity, more photons hit the cathode per second, emitting more electrons, so the current increases. But what if we change the wavelength to 5.5 times 10 to the negative 7 meters? We first calculate the threshold wavelength, which is about 6.2 times 10 to the negative 7 meters. Since our new wavelength is shorter than the threshold, electrons are still emitted. Because the intensity didn't change, the rate of emission stays the same, meaning the current remains constant.
Let's look at another example. Light of wavelength 5.9 times 10 to the negative 7 meters hits sodium, producing electrons with a specific kinetic energy. If we change the wavelength to 4.5 times 10 to the negative 7 meters, what is the new kinetic energy? First, we use the initial conditions to solve for the metal's work function, which comes out to 3.2 times 10 to the negative 19 joules. Then, we use that work function with the new, shorter wavelength to calculate the new maximum kinetic energy, resulting in 1.22 times 10 to the negative 19 joules.
In our third example, ultraviolet light of 250 nanometers falls on tungsten, which has a work function of 4.49 electron volts. To find the cutoff wavelength, we convert the work function to joules and divide Planck's constant times the speed of light by this energy, giving about 2.68 times 10 to the negative 7 meters. To find the stopping potential, we calculate the energy of the incoming 250 nanometer photon, subtract the work function, and divide by the charge of an electron. This yields a stopping potential of 0.4825 volts. For our final worked example in this section, we need to find the maximum speed of emitted electrons when violet light of 0.4 micrometers hits a surface with a threshold wavelength of 0.65 micrometers. We rearrange our photoelectric equation to solve for velocity squared, factoring out hc. Plugging in the mass of an electron and our wavelengths, we find the velocity squared is 4.199 times 10 to the power of 11. Taking the square root gives a maximum speed of 6.48 times 10 to the 5 meters per second. Here are the first few trial questions for you to practice. Question 1 asks for the maximum speed of photoelectrons from a cesium surface. Question 2 introduces beam power, asking you to relate milliwatts to the number of photons per second, and then calculate the resulting photocurrent, assuming an 80% emission efficiency. Question 3 works backward from a measured microampere current to find the energy of the individual photons and the source's total emission rate. The final trial questions challenge your algebraic skills. Question 4 requires you to set up a system of equations using the photoelectric formula to prove that the threshold wavelength is exactly 4 times the initial wavelength, given the specific drops in kinetic energy. Finally, question 5 is a straightforward calculation of stopping potential, given a work function in electron volts and an incident frequency. Work through these carefully to prepare for our upcoming discussion on the internal structure of the atom. Continuing our exploration of electromagnetic radiation, we turn our attention to X-rays. X-rays are a form of electromagnetic radiation, characterized by a very short wavelength. They are generated through a specific physical process. When fast-moving electrons are abruptly decelerated or stopped by colliding with a hard metal target, their kinetic energy is converted into these high-energy waves. The production of X-rays involves several precise steps. First, a filament is heated by a low voltage, causing it to emit electrons through a process called thermionic emission. These ejected electrons are then directed towards a target by a focusing cap. To give them high kinetic energy, they are accelerated by an extra high tension, or EHT, applied across the cathode and anode. When these high-speed electrons strike the target, a massive energy conversion occurs. Interestingly, about 99% of the electron's energy is converted into heat, while only a tiny fraction, about 1%, actually becomes X-rays. Because of this immense heat generation, cooling fins are required to remove the heat from the target. Additionally, the entire process takes place in a vacuum, ensuring that the electrons do not collide with air molecules and lose energy on their way to the target. If we trace the energy transformations during this process, it forms a clear sequence. It begins with electrical energy supplied by a low alternating current voltage. This electrical energy is converted into heat energy in the filament, which facilitates the release of electrons. Once released and accelerated, this energy manifests as the kinetic energy of the rapidly moving electrons. Finally, upon impact with the target, this kinetic energy is transformed into 2 forms, a large amount of heat energy within the target and the electromagnetic energy of the X-rays themselves. This diagram illustrates the internal structure of an X-ray tube. On the right, we see the cathode assembly, which includes the tungsten filament where electrons are generated, surrounded by a focusing tube to direct the electron beam. These electrons travel across the vacuum enclosed by the glass wall. On the left is the high-voltage anode, which houses the tungsten target. The electrons strike this target at a specific takeoff angle, producing X-rays that exit the tube through a specialized beryllium window. The design ensures efficient generation and direction of the X-ray beam, while managing the intense heat produced at the anode.
For an X-ray tube to operate continuously and effectively, it must incorporate several specific features. It needs a low alternating current voltage to heat the filament, which serves as the source of electrons. A high accelerating potential difference is crucial to give the electrons sufficient kinetic energy. The target must be made of a material with a very high melting point, like tungsten, to withstand the intense bombardment. To manage the 99% of energy converted to heat, a robust cooling system with cooling fins is necessary, and the anode itself is typically made of copper, a good thermal conductor, to draw heat away from the target. Finally, a vacuum environment is maintained so electrons travel unimpeded without losing energy to gas molecules. X-rays exhibit several distinct properties that make them useful in various applications. Like visible light, they affect photographic plates, which is the basis for traditional medical imaging. They travel in straight lines through space. Because of their high energy, they can knock electrons out of atoms, causing the ionization of gases they pass through. Unlike alpha or beta particles, X-rays carry no electrical charge, meaning they are not deflected by electric or magnetic fields. Furthermore, they can cause certain materials to fluoresce or emit visible light upon exposure. Continuing with their properties, X-rays have enough energy to cause photoelectric emission, meaning they can eject electrons from the surfaces of metals. Being electromagnetic waves, they travel at the speed of light in a vacuum and exhibit fundamental wave characteristics, such as diffraction and interference. One of their most famous properties is their ability to readily penetrate matter, allowing them to pass through soft tissues. However, they are strongly absorbed by very dense elements, such as lead, which is why lead aprons and shields are used for radiation protection. The penetrating power of X-rays refers to the extent to which the radiation can pass through matter. This property is directly controlled by the accelerating potential difference between the cathode and the anode. This voltage determines the amount of kinetic energy the electrons possess when they strike the target. The relationship is linear. Kinetic energy is proportional to the accelerating voltage, expressed as Ke equals E times V, where E is the charge of an electron and V is the voltage. It is important to note that increasing this accelerating voltage increases the kinetic energy of each electron and the resulting X-ray photons, but it does not change the total number of electrons reaching the target. It also increases the heat dissipated in the target. Based on their penetrating power, X-rays are classified into two categories, hard and soft. Hard X-rays are those with high penetrating power and correspondingly short wavelengths. Because of their high energy, they are often utilized in medical treatments, such as radiotherapy, to target and destroy cancer cells. On the other hand, soft X-rays have longer wavelengths and less penetrating power. These are the X-rays commonly used in standard medical photography to image the human body, as they provide good contrast between bones and softer tissues without excessive radiation energy. While penetrating power is about the energy of individual X-rays, the intensity of X-rays refers to the total power transmitted per unit area. Intensity is controlled by the filament current. By increasing the current flowing through the heating filament, its temperature rises, which in turn increases the number of electrons emitted per second. Therefore, a greater filament current results in more electrons striking the target, producing a higher number of X-ray photons, and thus a greater overall intensity. Changing the intensity in this way does not alter the penetrating power of the resulting X-ray beam. It is fascinating to compare X-ray production with the phenomenon of photoelectric emission, as they are essentially reverse processes. In photoelectric emission, incident electromagnetic radiation strikes a metal surface, transferring energy to electrons and causing them to be released, with very little heat generated. Conversely, in X-ray production, it is the fast-moving electrons that strike a metal target. Their sudden deceleration produces electromagnetic radiation in the form of X-rays, accompanied by the generation of a massive amount of heat. When we look at the spectrum of X-rays produced, we see specific spikes called characteristic lines. These originate from the atomic structure of the target material. At very high voltages, bombarding electrons can penetrate deep into a target atom and knock out an electron from an inner shell, such as the K shell. This leaves a vacancy, putting the atom in an excited and highly unstable state. To restore stability, an electron from a higher energy shell drops down to fill this vacancy. As it transitions to a lower energy state, it emits an X-ray photon.
The energy of this photon exactly matches the energy difference between the two shells. Transitions that end in the K shell produce the K series of X-ray lines, while those ending in the L shell produce the L series. Because these energy levels are unique to each element, these lines are characteristic of the specific metal used as the target.
In addition to characteristic lines, an X-ray tube also generates a continuous spectrum of radiation. This occurs because the bombarding electrons undergo various collisions with the target atoms, causing them to decelerate. During each deceleration event, the lost kinetic energy is emitted as an X-ray photon. Because the electrons decelerate by varying amounts, X-rays of many different wavelengths are produced. These overlapping wavelengths create a continuous background spectrum. The absolute shortest wavelength, known as the cutoff wavelength, occurs when a rare electron loses all of its kinetic energy in a single direct encounter with the target atom. Conversely, the longer wavelengths in the spectrum are the result of electrons losing their energy gradually over multiple successive collisions.
Let's examine the graph of X-ray intensity plotted against wavelength. The curve begins at a very specific point on the horizontal axis, denoted as lambda min, or the minimum wavelength. As mentioned, this point represents the scenario where a bombarding electron has a direct head-on collision with a target atom, losing 100% of its kinetic energy in a single encounter. This single, massive energy transfer creates the most energetic X-ray photon possible for that given voltage. Since energy is directly proportional to frequency and inversely proportional to wavelength, this maximum energy corresponds to the maximum frequency, and therefore the absolute minimum wavelength possible in the spectrum.
Moving to the right from the minimum wavelength, we see a broad, smooth curve. This is the continuous spectrum. It exists because the vast majority of bombarding electrons do not lose all their energy at once. Instead, a single electron will typically undergo a series of glancing collisions as it travels through the target material. At each collision, it loses a fraction of its kinetic energy, emitting X-ray photons of correspondingly smaller energies and longer wavelengths. Because there are countless electrons undergoing countless random collisions, these individual emissions overlap perfectly to produce this continuous, humped curve. Superimposed on top of the continuous curve, we observe sharp, distinct peaks. This is the line spectrum, consisting of the characteristic X-ray lines we discussed earlier. These peaks occur when bombarding electrons penetrate deep enough to displace inner shell electrons, causing the target atoms to become excited. As electrons within the atom fall from higher energy levels to fill these lower vacancies, they emit X-ray photons with very specific, definite frequencies. These prominent lines, such as the K series and L series, are entirely dependent on the atomic structure of the target metal. If we were to change the metal target, the wavelengths of these specific peaks would shift accordingly. Next, we will look at the experimental evidence for the wave nature of these X-rays. Let us look directly at the experiment that demonstrates the wave nature of X-rays. A narrow beam of monochromatic X-rays is directed through lead slits to collimate it, and then it strikes a crystal. The atomic spacing in the crystal is comparable to the wavelength of the X-rays. Behind the crystal is a photographic plate. When we analyze the plate, we see a central dark spot surrounded by a distinct pattern of smaller dark spots. This specific pattern is a diffraction pattern, which is a hallmark of wave behavior, confirming that X-rays indeed travel as waves. Beyond diffraction, there are several other reasons we classify X-rays as electromagnetic waves. First, they produce line spectra, which is characteristic of electromagnetic radiation interacting with atomic energy levels. Second, they can eject electrons from matter through the photoelectric effect, meaning they have enough energy to ionize gases. Finally, they are produced by accelerating charged particles, specifically electrons, which perfectly aligns with Maxwell's theory of electromagnetic radiation. Because of their high penetrating power, X-rays have crucial industrial applications. In the art world, they are used to look beneath the surface of a painting to verify its authenticity or reveal earlier drafts. In engineering and manufacturing, X-rays act as a non-destructive testing method. They can reveal microscopic and visible cracks inside solid metal castings, welded joints, and even thick rubber motor tires. Additionally, as we will explore deeply, they are used to study the internal atomic structure of crystals. In biology and medicine, X-rays are an indispensable tool. They are widely used for medical imaging to examine internal organs, check lungs for diseases like tuberculosis, and most commonly to photograph broken bones. But they are not just for imaging. High-energy X-rays are also used therapeutically to target and destroy cancerous cells and other malignant growths within the human body. While incredibly useful, X-rays carry significant health hazards because they are a form of ionizing radiation. prolonged or unprotected exposure can destroy healthy body tissues, damage blood cells, and severely impair eyesight. Furthermore, if X-rays damage the DNA in reproductive cells, they can cause genetic mutations that produce changes in subsequent generations. This is why lead shielding and strict safety protocols are always used.
It is important to distinguish X-rays from the cathode rays used to produce them. X-rays are massless electromagnetic waves traveling at the speed of light, whereas cathode rays are actual particles, specifically fast-moving electrons, which travel much slower. When X-rays hit matter, they eject electrons. Conversely, when cathode rays hit matter, they produce X-rays. Because X-rays have no charge, they cannot be deflected by electric or magnetic fields, unlike the negatively charged cathode rays. Similarly, we must differentiate X-rays from beta particles, which are high-energy electrons emitted during radioactive decay. The distinctions are nearly identical to cathode rays. X-rays are uncharged electromagnetic waves moving at the speed of light. Beta particles are negatively charged electrons, move slower than light, and are greatly deflected when passing through electric or magnetic fields. Since we cannot see X-rays with our eyes, we rely on specific instruments to detect them. The most traditional is the photographic method, where X-rays expose a film plate just like visible light does. We can also use an ionization chamber, which measures the electric current created when X-rays ionize a gas inside it. For more precise counting of X-ray photons, a Geiger-Müller tube connected to a rate meter is highly effective. Now we arrive at a fundamental principle of crystallography, Bragg's law. When X-rays scatter off the atomic planes of a crystal, they interfere with each other. Bragg's law states that constructive interference occurs when the path difference between waves reflecting off adjacent planes equals an integer multiple of the wavelength. Mathematically, this is expressed as 2d sine theta equals n lambda, where d is the plane spacing, n is the diffraction order, and theta is the glancing angle. To understand where Bragg's law comes from, let's look at the geometry of the scattering. Consider a beam of monochromatic X-rays incident on a crystal. A small fraction of the X-rays is scattered by atoms in the top plane, P1, and some penetrate to scatter off the next plane, P2. The scattered rays will only form a strong, detectable beam if they interfere constructively. This happens when the angle of incidence equals the angle of reflection, making the scattered rays parallel. Looking at the geometry from the previous diagram, the X-ray hitting the lower plane travels an extra distance. This path difference is the sum of the segments AB and BC. Using basic trigonometry, since the distance between planes is d, both AB and BC are equal to d sine theta, so the total path difference is 2d sine theta. For constructive interference to occur, this path difference must exactly equal an integer number of wavelengths, n lambda. Equating the two gives us Bragg's law, n lambda equals 2d sine theta. There are a few critical details to remember when using Bragg's law. First, the glancing angle theta is measured relative to the crystal surface itself, not the normal line as we usually do in optics. Second, the sine of an angle cannot exceed 1. Therefore, to find the maximum possible order of diffraction, we set sine theta to 1, giving us 2d equals lambda times n max. Similarly, the absolute maximum wavelength that can be diffracted by a crystal occurs at the first order, when sine theta is 1, meaning lambda max equals 2d. We can use macroscopic properties like molar mass and density to calculate the microscopic atomic spacing, d, of a crystal. Let's take potassium chloride as an example. The mass of one ion pair is the molar mass divided by Avogadro's number. Dividing this mass by the crystal's density gives the volume of one ion pair. Since potassium chloride has 2 ions per pair, the volume occupied by a single ion is half of that. If we assume the atoms form a simple cubic lattice, the volume of one ion is d cubed. Taking the cube root gives us the exact spacing between atomic planes. Let's apply these concepts to some worked examples. In this first problem, an X-ray tube operates at 30 kilovolts with a current of 2 milliamps. We need to find the electrical power input. We start by converting our units to standard SI units, 30,000 volts and 0.002 amps. Power is simply current times voltage. Multiplying 0.002 by 30,000 gives us a total electrical power input of 60 watts. Next, we find the number of electrons striking the target per second. Since current is the rate of charge flow, we divide the total current by the charge of a single electron. This gives us 1.25 times 10 to the 16th electrons per second. For part 3, to find the speed of the electrons, we equate their maximum kinetic energy to the electrical work done on them, EV. Rearranging for velocity and plugging in the mass of an electron and the 30,000-volt potential, we find they hit the target at an incredible speed of 1.027 times 10 to the 8th meters per second.
The final part of this example asks for the lower wavelength limit of the emitted X-rays. The shortest wavelength corresponds to the highest energy photon, which occurs when an electron transfers all its kinetic energy into a single X-ray photon. We set the photon energy, hc over lambda, equal to the electron energy, eV. Rearranging for lambda minimum and plugging in Planck's constant, the speed of light, electron charge, and voltage, we get a minimum wavelength of 4.144 times 10 to the negative 11 meters. In our second example, we deal with the inefficiency of X-ray production. 90% of the input power is lost as heat, which is given as 742.5 watts. This means the total input power is 742.5 divided by 0.9, or 825 watts. Dividing this total power by the 75 kilovolt potential gives a current of 0.011 amps. Dividing that current by the elementary charge reveals that 6.875 times 10 to the 16th electrons arrive per second. If we increase the voltage, the electrons will hit with more kinetic energy, generating more heat and higher energy X-rays, but the actual number of electrons flowing per second will not change.
Let's look at a direct application of Bragg's law. We are given a sodium chloride crystal with a plane spacing of 2.82 times 10 to the negative 7 meters. A first-order reflection is observed at a glancing angle of 15.8 degrees. We need to find the X-ray wavelength. We simply plug our values into the Bragg equation. N lambda equals 2d sine theta. With n equal to 1, we multiply 2 times the spacing times the sine of 15.8 degrees, yielding a wavelength of 1.536 times 10 to the negative 7 meters. In this comprehensive example, we combine Bragg's law with our atomic spacing formula. First, we use the given wavelength of 1 times 10 to the negative 10 meters and the angle of 10.2 degrees to find the plane spacing, d, which calculates to 2.824 times 10 to the negative 10 meters. Next, we find the molar mass of sodium chloride in kilograms per mole. Using our density formula derived earlier, we plug in the molar mass, Avogadro's number, and our calculated spacing cubed. This reveals the density of the sodium chloride crystal to be 2,157 kilograms per cubic meter.
To master these concepts, you should work through these trial questions. They will test your ability to calculate heat transfer and cooling systems, determine minimum wavelengths from electron energies, and apply Bragg's law to find glancing angles and interplanar spacing in different crystals. Practice is essential for solidifying the relationship between electrical power, electron kinematics, and X-ray diffraction.
To wrap up our discussion, remember that X-rays perfectly illustrate wave-particle duality. They are electromagnetic waves that can be diffracted by crystal lattices. Bragg's law is your primary tool for connecting the measurable angles of this diffraction to the invisible atomic spacing of materials. Understanding the energy conversions inside an X-ray tube allows us to harness this power safely for a wide array of industrial, medical, and scientific applications. Keep reviewing your formulas and keep practicing.